We're going to do our first full hypothesis test here. A 1996 report from the U.S. Consumer Product Safety Commission claimed that at least 90% of all American homes have at least one smoke detector. A city's fire department has been running a public safety campaign about smoke detectors with posters, billboards, and ads on radio and TV and in the newspaper. The city wonders if this effort has raised the local level above the 90% national rate. Building inspectors visit 400 randomly selected homes and find that 376 have detectors. Is this strong evidence that the local rate is higher than the national rate? So there's some important information, okay?
So is our null hypothesis?
Our P naught is 0.9. That's what they're telling us the national average is. Okay. And we want to know if this city's average is higher than that national average based on their new campaign. So then we have a P naught, that's going to be our hypothesized value, and we have a P hat. Our P hat is 376 over 400. Which is 0.94. So clearly that percentage is higher. What you're testing with the hypothesis test is this difference statistically significant? Is that difference large enough to believe that in that city the proportion of homes with a smoke detector is higher than the national average? Obviously, we see a difference in our sample to the hypothesis, right? But what's the probability that we get this sample if the true proportion is still 0.9? If that probability is small enough, then we reject the null hypothesis. All right. So the first thing we're going to do is write our hypotheses. H naught is that P equals 0.9. Or 0.90. Our null hypothesis is status quo. The city's proportion is the same as the national average. Okay? We never use our P hat as our hypothesis. Our alternative, now it says it wants to know if the local rate is higher, so is that P is greater than 0.9. And we're going to check conditions. It says that the houses were randomly selected. So the sample is random. We're going to assume that 400 is less than 10% of all homes in this city. If there was not, they probably wouldn't have the money to run a big campaign about having smoke detectors. And then the last, now I've switched to black, is that NP and NQ is greater than or equal to 10. What is my NP, my number of successes? Do I need to calculate that? 376. Wait. If we were doing a confidence interval, this would be our number of successes. But we're not doing a confidence interval. We're doing a hypothesis test. So we don't believe that this is true yet. We don't believe yet that this is the actual proportion. We want to know, in 400 homes, is 90% of those homes greater than or equal to 10? So when we check our NP and NQ for a hypothesis test, we have to use our P naught. Not our P hat, which is different from the confidence interval. Okay? So this is 400 times 0.9. and 400 times 0.1, which is 360 and 40. And then we can say since conditions are met, a normal model is appropriate. And we're going to name our test. I will use a one proportion z-test. We're doing a z-test. Okay. Questions so far? Okay, so we had conditions on the last page. Now let's talk about the mechanics of this test. Okay, the z-score was always the sample minus the population mean over standard deviation. Okay. In this case, our sample is p hat minus p naught, our hypothesized value, over the standard deviation, which is p naught q naught over n. Okay. We're operating under the assumption that the null hypothesis is true until we prove otherwise. So the p's that we are using in all of our calculations are the 0.9, the p naught and the q naught. And our p hat was 0.94. So let's create our standard deviation for the model, 0.9 times 0.1 over 400. So this is 0.015. And let's draw a little normal model here. So remember, we add 0.015 and then we subtract it. And our model is centered at 0.9. But what we're interested in is 0.94. Here's our p hat, 0.94. And this area represents the p-value. The probability of getting our sample of 0.94 if the actual proportion in that city was 0.9. So the test statistic is what we have been calling the z-score. So that calculation, oops, wrong, is 0.94 minus 0.9 over 0.015. Please notice that the calculation's not any different than what we did in chapter 18 and what we did in chapter 6, right? Your sample minus the mean divided by standard deviation. That's not changing. We might change the variables and the way it looks in here, but it's still the same general idea, sample minus the mean divided by the standard deviation. And the standard deviation calculation changes a little bit here and there, but for the most part, it's the same general idea. For proportions now, it's that square root p hat q hat over n, or pq over n. And then for standard mean and standard deviation, we'll talk about that later. So this is 0.04 divided by 0.015 is 2.667. That is our test statistic, our z-score. And to get our p-value, we do something we've always done. Normal CDF, 2.667, 99, because it wanted greater than. My alternative hypothesis is what determines whether it's greater than or less than. Do I do my z-score, 99 when it's greater than? Yes, my z-score, 99. If it was less than, I would do negative 99, my z-score. So that alternative hypothesis determines that. And then we'll talk about what to do and how it's different if it's not equal to. Okay. So we get, let's see, 99, 0.00383. So those are your mechanics. Drawing the model helps us see what we're actually finding, right? The middle of the model should always be your p-naught. And then the area you're shading represents what that p-value is for your sample. So now we can write a conclusion. So our p-value is small, right? 0.003. This is a 0.38% chance of obtaining our sample if the null hypothesis were true. So here we're going to interpret our p-value. That's not big enough. So, interpreting our p-value. I have seen free response questions where it just asks you to interpret your p-value. Okay, so this is a really important concept. Do you really understand what you're calculating? This is the probability of getting our sample if the null hypothesis were true. So, this is how we're going to state it. I'm going to try to stay consistent with the poster I have up there. So, if the true proportion can't spell. I can't spell. Proportion of homes, I don't like this keyboard, with a smoke detector is 0.90. Okay. If the proportion, because we're talking about proportions, there's our context. Homes with a smoke detector is our p-naught, our hypothesized value. There is a 0.00383 chance of obtaining a sample proportion, hold on. A result as surprising or more surprising than 0.94. Okay, so here's our conclusion. Since my p-value of 0.0038 is so small, we're not going to talk about an alpha level yet, like you see on the poster on the board. We're just going to say it's really small, so we reject. It's too big, so we fail to reject, okay? I reject the null hypothesis. There is enough evidence to convince me that the proportion of homes with a smoke detector is not 0.9. And we could add in this city, because we're only talking about the city we took our sample in. We don't think it's 0.9 anymore. The probability of getting our sample is too small. So now we can create a confidence interval. Okay?